Okay, this video is about how we integrate under a curve, and for this problem it's under the curve that we see for a depth profile for respiration and prime production. Now this video is about doing that for prime production respiration for the water column, and hopefully will help you do the homework that's due on Friday. But I hope you also learn some general ideas about how we do this in real life with other types of data. There are many cases where we measure something and we want to extend that and integrate it and add it all up for an extended amount of time. For example, we may measure a rate every hour or 6 hours, and do that for a week. Those rates will vary over that time period, and but we want to get some integrated value for that whole 2 weeks, let's say. So that's kind of the same idea that we're faced with here, with looking at these rates as they vary through the water column. So let's first start with the easy problem, and that is that of respiration. At least for this problem, respiration is easy. So let's consider a water column and with respiration with units of, let's say, milligrams of carbon per meter cubed per day. Now actually in real life we usually use per liter here, but we're going to keep the meter cubed to make it a little bit easier, because over here we have meters, depth expressed as meters. Now for the homework, and what Sverdrup originally assumed was that respiration was constant with depth. And so that makes it really easy to get an integrated rate of respiration, because if we think about trying to find the integrated rate of respiration down to, say, 100 meters, we have a rectangle here. And you should know from grade school, right, how to find the area of that rectangle. It's basically the depth here, which is 100 meters, times the value of the respiration, which let's say is 15 milligrams of carbon per meter cubed per day. So we multiply that times 100 meters. The area of a rectangle is basically one side, the length of one side multiplied the length of another side, and we get 1,500 milligrams of carbon per meter squared now per day. So notice the meters here cancels out one of the meters cubed, and we are left with meters squared. So that was the easy example. Now let's consider a bit harder example. That is photosynthesis. Photosynthesis does not vary regularly, or it does not vary, is not constant with depth, but rather it varies with depth, even in Sverdrup's model. So now if we consider photosynthesis or prime production here, and in the homework problem, basically you have to calculate the rate of prime production as it varies with depth, given the assumption about the depth, the attenuation coefficient, and what the value of prime production is at the surface. But you should already know that prime production kind of varies like so with depth. That is, as the light decreases, to make points, there are a couple more points, we don't need to know all those points. It varies something like that. Now, so you should be able to calculate that in the homework. That's one thing you're going to have to figure out how to do. So this video, though, is about how do we now calculate the area the area in here. That is, figure out the integrated rate of prime production down to some depth. And we'll again pick 100 meters here. So now, but we're going to do the same thing. So we're basically going to divide this curve here, this area under this area right here, into a bunch of little rectangles that we know how to calculate the area for. We don't know how to calculate the area here directly, but we can divide it into rectangles where we do know how to calculate the area. And basically what we're going to do then is say, okay, well, let's take some depth here so we know the depth. And it's easiest just to always take the most same depth, and I think in the spreadsheet I sent you, I set that as 5 meters. That's supposed to be a straight line there. And what we're going to do is make the rectangle such that it's the average of these 2 points here. So the value that's given here then is basically the average of that point say A and that point B. And so A plus B, the average of those 2 points is just A plus B divided by 2. And so the area of this little rectangle here then is basically 5 meters times those two values. So let's say the first value is 20 milligrams per meter squared, per meter cubed per day, and the next one is 15 milligrams of carbon per meter squared, per meter cubed per day. So now we have to take the average of that, and that's going to be a little hard. So that's 35 divided by 2. Ooh, what is that? Roughly about 35 divided by 2 is maybe 17 or so, roughly. And times that by 5. Should have picked an easier example. Of course, in a spreadsheet, you can do this by let Excel do all the hard arithmetic. And we get stuff roughly 80 milligrams of carbon per meter squared per day. So again, the same thing. The units here are meter cubed, multiplied by meter times meters, and this we get meters squared. That's for that box. Now we have to do the next box, and then we do the same thing. We take, again, the depth interval here, take the average, and again, we find the area for that. And we do the same thing. So now we know the area for that. We keep on doing that, and then we need to, that's finding the area for each individual rectangle here. And then we have to add them up. Now you notice that this is an approximation of the true area that's given here, because the area that's, let's erase this and start over here, make this a little cleaner, sorry. So to get the true area, get the area, we have to add up all those little boxes, right? And that's what's done in the spreadsheet in the example that I showed you, I sent to you. So this whole video is to give you a bit more intuitive idea what's going on. But let's look again of why this is not too bad of an approximation for the true area for that particular wedge. So if we take this example here, the true area would be basically something that would go like this, right? And we find it, but I don't know how to calculate this, right? Maybe I could figure it out, but I'm not going to try to do it that way. Instead, again, I'm going to take the average, and so the average is something like this. And so if you think about it, what's happening here is that by taking the average, we are kind of underestimating we're missing this part of the area, but we're gaining this part. Everyone see that? Let's try that again. Let's make it a little bit bigger. So again, if we take the average of the two, the true area would be something like this. But in fact, what we're doing is by taking the average of these two values, we're taking a little bit of this area, but we're losing out on that. And so the two of them kind of cancel out, making the triangle a bit of it's a pretty good approximation for what that true area is under that in that curve there. And so by doing that several times through the depth profile, we can get a pretty good approximation for what the true integrated rate of prime production is in this particular example. So I hope that gives you some intuitive feel for what's happening when we try to do integration with these type of data. And I hope that will help you answer the homework problem.